My name is Kirill. I'm software engineer on Facebook video team. I'll be later joined by my colleague Nitin. Today we would like to talk to you about new live video delivery system we've been working on. Live videos have become an important part of Facebook ecosystem, and we've built many different products based on Facebook Live. Few examples are live quiz, game shows, watch party, live shopping, and many more. Different products have different requirements, and having extensible and flexible infrastructure is very important to be able to support that. In this presentation, I will talk about generic live video delivery stack, talk about challenges that we encountered as we were evolving Facebook Live video delivery system, and introduce an alternative architecture that we've been working on and highlight key components and features. Let's talk about main components that we would need if we were to build new live video delivery system from scratch. There are four high-level components: production, ingest, processing or encoding, and delivery. In this talk, I would like to focus on the last component, delivery. Most live video delivery systems today use manifest-like delivery format Dash or HLS and consist of players, CDN to provide scalability via caching, and live server that plays middleman between live ingest and delivery. Let's look at typical steps required for playback in such system. First, we need a URL for manifest. Given the URL, player makes an HTTP GET request to the server. Server receives the HTTP GET request and checks this cache, and if data is there, it serves data from the cache. If not, it goes to the next hop, and so on and so on. And in some cases, it will go all the way to the live origin. From the manifest, player needs to decide which bitrate lane to use. Once bitrate is decided, player can fetch init segment for audio and for video. Is also required to initialize decoders. After that, player can fetch actual audio and video segments using the same CDN flow, and we are ready to play. Not counting initial URL fetch, it can take up to 5 HTTP requests and 5 RTTs before player can even start playing first frame. Optimizations can be done to reduce number of HTTP requests and RTTs required, but it's up to the player implementation and it needs to be done on all platforms. In order to continue playing, player would need to refresh manifest. And the whole process would continue except for init segments. There could be multiple reasons why we would need to refresh manifest. Timeline might have changed. There could be gaps in segment IDs if special templated version is used. People nowadays consume video on different platforms: mobile, desktop, TVs, and in different network conditions: home Wi-Fi, mobile internet. Playing well in different network conditions can be challenging, and the common technique to achieve that is to use ABR, adaptive bitrate. In traditional system, multiple qualities are advertised in the manifest. Player estimates available bandwidth and makes a decision when to switch qualities when it's needed. Switch can only happen at GOP boundaries. Usually all qualities have the same GOP interval. Larger GOPs are desired for better compression efficiency. Switch point may be too far, hence possible risk of stall. Here is an illustration of such problem. Playback position is at the beginning of the segment. With 10-second segment size, player can only switch in 10 seconds. So player can either jump and skip over current segment, or it can keep playing current undesirable bitrate and then request segment at lower quality. This is usually not such a big problem for players since they build up buffers specifically to accommodate network changes. However, it can become a problem when lower latency is required or when buffer size is smaller than GOP size. ABR decisions are made on the client, so players on all platforms need to implement pretty much the same logic. Speaking of low latency, common technique for Dash or HLS type of playback systems is to leverage HTTP chunk transfer and CMAF. I'm not going to go into details of how it's done. There are multiple online resources on this topic. However, with chunk transfer, player can no longer estimate available bandwidth by just observing how fast it can download segments. Since segments are going to be downloaded at best at the rate they are being produced. So we need a different bandwidth estimation algorithm, and it needs to be implemented on all platforms again. It's not uncommon for processing or encoding to have slight variations. Sometimes it may take a little bit longer than real time to encode chunk. That means it's possible that by the time the player needs to switch quality, chunk is not available. I've talked about the problem that player can only switch at segment boundaries. For low latency, that can lead to stall. If current quality has higher bitrate than available bandwidth, player could want to cancel current HTTP requests and switch to lower quality immediately. The problem is that CDN may have written few remaining chunks by that time, and there is no way to cancel those in-flight bytes. Also, to achieve low latency, player needs to carefully time network requests. So let's summarize. Dash and HLS are widely adopted formats. Traditional pool-based system is complex and can be suboptimal for cases where low latency is required. Same EBR logic needs to be implemented on multiple platforms. There are trade-offs between how fast player can switch qualities and compression efficiency. Low latency is generally hard. In order to address problems that I described and more, and to support different product requirements that I've talked at the beginning, we've been working on a new live video delivery system. We called it Rush. It's still work in progress and things likely will change. I'd like to hand it over to Nitin to talk to you more about Rush architecture.
Thanks, Kirill. I would love to talk about the Rush architecture. At high level, Rush has the same components as a traditional architecture. It has a live server, it has CDN running on origin and edge, and it has players. However, there are a few key differences. First, let's start with understanding how playback flow works. Player makes a request to get a URL, same as before. Then it uses the URL to make an HTTP GET request to CDN, also same as before. However, at this point, things start to differ. CDN uses the URL to look up the audio and video data in the cache. If it does not get the data from cache, it makes a request to origin. Once it has the data, it starts streaming it back to the client, and the player is ready to play. That's it. Now you might remember for a traditional design, it takes multiple RTTs for a client to start playback, and the client needs to make a lot of requests during the course of the playback to continue playing. However, in case of Rush, you only need to make one request with the subscription URL to start playback, and you don't have to make any other request during the playback. You can continue playing as long as you want. Now, you might be wondering that this sounds good in theory, but how does it all work? Where is the manifest here? What does CDN actually send to the player and how? And is there any ABR at all? We will answer these questions one by one in the following slides, starting with the manifest. Technically, you don't need a manifest to do the playback. All you need to know is how many tracks are there in the video. Usually there are just two, audio and video. Then you need to know what is the codec used and what is the timescale. You can call that information a manifest. In our case, CDN sends the manifest in the form of JSON to the client, and it looks like this. You can notice here it has the information about each track, it has the timescale and codec information. Besides that, it also has information for qualities, but that's not really needed by the player to do anything. It's mainly just for logging purposes. Now let's understand what CDN sends to the player and how. Like I described before, player just needs to make one request with subscription URL to start the playback. And it does not need to make any other request after that. CDN uses HTTP push to send the data to the client. HTTP push is a functionality which allows server to initiate an HTTP transaction and send a resource to the client without client having to request it ever. CDN uses HTTP push to push the manifest, audio, video metadata, and all the audio and video frames. To send the data, CDN uses our own container format. In this container format, there are two cacheable physical entities. One is called metadata and the second is called data. Data entity basically contains encoded stream of bytes. For audio, the data entity might contain AVC bytes, and for video, it might contain H.264. Metadata contains meta information about the data stream. More specifically, metadata stream has fixed size records where every record represents a frame. The record points to a frame in the data stream, and it contains information such as what is the offset of the data frame in the bit stream, what is the length of the data frame, what is sequence ID, timestamp, and some other flags. Together, its size is about 36 bytes. Now, having this container format allows us to achieve two things. Number one, it allows us to address each frame individually. This means we can play a video as soon as we are downloading it with minimum delay. And we are able to do it with less overhead as compared to other options. With fragmented MP4, doing something similar is possible, but you will need to have one move atom per frame, which will be about 100 bytes. That can translate to more than 20% of overhead in low bitrate scenarios. In contrast, with Rush, we only have 36 bytes per frame overhead. Second, it allows us to enable lossy playback. Now imagine you are on a lossy network and you happen to have some packet loss. Because of packet loss, maybe you lost some frames in your bit stream. Now, because the metadata records are fixed size, even if you lost record for F2, you can still parse F3 and F4. And correspondingly, you can look up the frame in the data bit stream, frame 3 and frame 4. And if possible, you can parse, you can decode, and you can play those frames. This allows us to enable WebRTC like lossy playback scenarios, which can be very, very useful for low latency. We do have ABR. ABR is running on the last CDN node closest to the client. When the ABR algorithm decides that it's time to switch, it looks up the new quality in the cache. If the quality is available in the cache, it starts streaming it to the client right away. If the quality is not available in the cache, it makes a request to origin, and as soon as it starts getting the new quality, it starts sending the new quality to the client. Now, having the ABR on the server allows us to achieve a few things. First, we are able to switch qualities without player making any additional requests at all. This ensures that our players can be kept dumb and very, very simple. And it also reduces the need to have additional communication overhead between client and server. Second, we are able to share the ABR logic across all platforms. This can be especially advantageous for mobile clients where shipping any new change can take minimum days to maximum in the order of weeks, because you have to write your new code, you have to create a new build, and you have to submit it to the App Store for approval. With having the ABR logic on the server side, we are able to push and test a new change in the matter of hours. Third, we are able to change our ABR algorithm on the fly, and we can use an ABR algorithm which can be more suitable for a given requirement. For instance, for low latency use cases, we are able to use Google congestion control algorithm, which is used by WebRTC. We are able to use signals not just from the client, but also from the server in the ABR decisions. For example, there are some useful signals on the server about ingest stability, CDN load, and low-level transport stats from the socket, which can be really useful in ABR. For instance, if your CDN node is overloaded, you may want to prefer the quality which is already in the cache, and you may not want to fetch a new quality and increase the CDN load even more. Similarly, because CDN node has access to the socket, it has information about packet loss, congestion window, and RTT, which can make your ABR algorithm more reactive to congestion. It also allows your ABR algorithm to become more dynamic. For instance, if your encoding capacity is overloaded, you may want to stop production of a certain quality. Now you can do that very easily. You can just send a manifest update to the CDN and have CDN remove that quality from consideration. Last but not the least, you're able to achieve better compression by having larger GOPs and removing the restriction of only switching at GOP intervals. You can do that by having different qualities, different GOP sizes, and unaligned GOPs. With that, you can have larger GOPs, better compression efficiency, and you can switch to a different quality which happens to have a GOP boundary before the GOP boundary for your current quality. This allows you to get the best of both worlds. You can get better compression quality and you are not sacrificing on the ABR reactiveness. Now let's talk about low latency. Low latency is an important part of Rush design. In Rush, player makes a request with subscription URL which goes all the way to the live server. Live server is a middleman between ingest and egress. When live server starts getting data from ingest, it can start streaming the fresh frames back to the client right away. This removes the need to do any timing from the client as needed in the traditional design, and we can make sure that the frames are being sent to the player with minimum latency possible. For even lower latency scenarios, you may want to have more fine-grained control. That is also possible with Rush. What you can do is, after you write a frame to HTTP body, you can set a delivery timeout. Once the delivery timeout fires, if you have not gotten the acknowledgement for the frame, you can simply cancel the transmission for the frame. If you do that for every frame, you can make sure that all frames get an equal time to be transmitted, and you can make sure that none of the frames are taking more time than the desired latency for the application. This requires support from HTTP and transport, but it can be done. Now, remember that CDN in our case is running ABR, and it has a lot of information about the media. You can utilize that to make even smarter decisions about latency control. For instance, you may want to give important frames in the GOP, such as keyframe, more time to be transmitted, and you may want to give other frames, such as a B frame, less time to be transmitted. That is also possible with Rush. In addition, you can also simulate WebRTC-like on-demand retransmission scenarios. At this point, I would like to hand it back to Kirill to summarize.
Thank you, Nitin. We can keep talking for hours, however, unfortunately we are running out of time. Let's summarize. With Rush architecture, player CDN interactions become simple. ABR can run on a server. It doesn't have to, but there are benefits, and it enables a number of optimizations. It enables per-frame latency control similar to WebRTC. Same architecture can be used for VODs and can scale to millions and millions of viewers, same as Dash. Adopting this design for clients running in browsers can be hard. It requires new APIs to access low-level transport primitives. It was difficult to talk about Rush in the past because we were talking about theory. Now that we have some deployment experience, we would like to talk about it more, especially with the folks working on standards. If you want to learn more about server-side ABR, or if you want to know details about CDN components that we had to build, or you're a browser developer and you're interested in enabling this design for clients running in browsers, or if you have any other questions, please reach out. And that's all we have. Thank you.